Hello everyone, we are students from Group 5 of SSC 1793 Section 40. First of all, let me introduce our group members. I am LIANG and my group mates ZAIDATUL NISHA, HANEES MARISYA, NURULFATIHah, Chongli, and KHALIL. What is linear differential equation? The general form of a linear differential equation can be expressed in the form of this, where these terms are called coefficients and fx is a function in terms of x. If fx equals to 0, then the equation is called linear homogeneous equation. If fx not equals to 0, then the equation is called linear non-homogeneous equation. In this topic, we have learned method to obtain solutions to homogeneous equation and non-homogeneous equation. For solving non-homogeneous equation, we have learned method of undetermined coefficients, strategies on solving higher order linear ordinary differential equation, and also method of variation of parameters. Last but not least, application of second order ODE on mechanical vibration and RLC circuit are discussed in this topic. For homogeneous equation, first of all, we have to make sure that the fx is equal to 0. Then, we have to obtain the characteristic equation. The power of the terms in characteristic equation is based on the derivative of the equation. The coefficient of the differential equation is maintained in the characteristic equation. Then, from the characteristic equation, we can find the roots and identify the types of roots to get the general solution for different cases of roots obtained. For roots of case 1, real and distinct, the general solution will be y equals to a exponent mx plus b exponent mx. Case 2, real and equal roots. The general solution is y equals to exponent mx times a plus bx. Case 3, complex numbers, roots, and the general solution is y equals to exponent alpha x times a cos beta x plus b sin beta x, where alpha is real roots, beta is imaginary roots.
Hi, my name is KHALIL and I'm going to explain about solution to non-homogeneous. The solution to the non-homogeneous equation ay double prime plus by prime plus cy equal to fx is given by yx equal to yhx plus ypx. The yhx is the solution of the homogeneous equation. Ypx is called the particular integral. There is two methods to find ypx. First, methods of undetermined coefficient, and second, method of variation of parameters. For methods of undetermined coefficient, the form of yp depends on the form of fx. There are 4 cases for the method of undetermined coefficient. First, for the case 1, polynomial of degree n. Second, case 2, form of CE power of mx where c and m are constants. For the case 3, sine and cosine function. For the case 4, sums or product of the above function. Case 1, 2, 3. 5. Choose the smallest r. Mean of r equal to 0, 1, 2. Chosen to ensure that no term in ypx is in the corresponding yhx. This is the example of for the case 1, for the case 2, for the case 3, and for the case 4.
Method of variation of parameter have total of 5 steps. Step 1 is identify alpha and fx in the differential equation. Step 2 is Consider whether the differential equation is homogeneous equation. If it is homogeneous equation, choose the y1 and y2. Step 3 is find the Wronskian. The Wronskian formula is Wronskian is equal to y1 times with y2 prime minus y2 times with y1 prime. Step 4 is find the u and v, where u is equal to negative integrate y2 times with fx divided by alpha times with Wronskian dx plus c. v is equal to integrate y1 times with fx divided by alpha times with Wronskian dx plus d. Step 5 is the general solution for particular solution of differential equation is given by y is equal to u times with y1 plus b times with y2.
This second order differential equation describes the balance between the inertia of the mass, the damping force, and the spring force. The solution to this differential equation provide information about the motion and behavior of the system, such as it helps in analyzing the natural frequencies of vibrating systems. Second, determining the amplitude and phase of vibrations. Third, studying the transient and steady state responses. And four, understanding the effects of damping on the system's behavior. For example, we can determine the natural frequency at which the system oscillates by solving the second order differential equation for a mass spring system. This information is crucial in designing structures to avoid resonance, which can lead to excessive vibrations and potential failure. Other than that, the solution of the second order differential equation also can help us understand phenomena like force vibration, where an external force is applied to the system, resonance, where the system responds strongly to an excitation at its natural frequency. In summary, related between second order differential equation with application of mechanical vibration allows us to model and analyze the behavior of vibrating systems, providing insights into their natural frequencies, damping effects, and responses to external forces.
My name is ZAIDATUL NISHA, and I'm going to present about the application of second order in mechanical vibration. To apply the second order differentiation into mechanical vibration, first we need general equation. The general equation is my double prime plus by prime plus ky equal to f function of t. The variables are m is mass, b is the damping coefficient, k is the spring constant, and function of t is force or external vibration that is applied to the system. There are four different types of vibration in the mechanical vibration application. First is undamped free vibration. Second is damped free vibration. Third is undamped forced vibration. And fourth is damped forced vibration. First is undamped free vibration. Undamped free vibration means there is no damping and no vibration involved. So B, which is stand for damping coefficient, should be 0. So the second order differentiation equation that we need to apply into this application is my double prime plus ky equal to 0. By solving using this equation, we will have the homogeneous equation. Next is damped free vibration, which means that it has no vibration involved, but damping still available. So the function of t only should be 0. So the equation that we need to be used in this situation is my double prime plus by prime plus ky equal to 0. By using this equation, we will be able to have the homogeneous equation. The third is undamped forced vibration, which means that it has no damping involved. So the equation that is need to be used in this situation is by double prime plus ky equals to f function of t. B is 0 because there is no damping involved, but there is vibration. That's why function of t is exists. By using this equation, we will have the homogeneous equation. The last situation is damped force vibration. That means that all elements are involved. There is vibration and there is damping. So the equation that need to be used is my double prime plus by prime plus ky equals to f function of t. By using this equation, we will have the homogeneous equation.
Let's move on to the example of mechanical vibration, which is the vibrating springs. As seen from the example 1, the question asks us to find the position of the mass at any time t, given the mass 5 kg, the x 0.2 meter, which obtained by subtracting 0.7 meter with 0.5 meter, the force of 25.6 Newton, and the initial velocity of 0. As seen in the next slide, those are the formulas related to the spring vibration. Next, to solve this question, we have to determine the k value by substituting the value of x and the force, then substitute m in the equation 1. Next, substitute the value of omega in equation 2, which can be obtained by square root of k over m. After that, given the initial condition of t equal to 0, x equal to 0.2, then C1 will be equal to 0.2. Differentiating equation 2, we will get x prime t equal to negative x C1 sin egg t plus x C2 cos egg t. Since t equal to 0, x prime equal to 0, and C2 equal to 0, then we will finally get the solution of xt equal to 1 over 5 cos egg t as the final answer.
Thanks for watching our video. We are from Group 5. Bye!